So assume that you have unknown distribution, P and Q, that you know from samples, IID samples. And what you want to estimate is the Wasserstein distance between P and Q. But you only know P and Q by the knowledge of the IID samples. And the question is, okay, so I am going to be interested in the Wasserstein 2 distance. So I need to recall the definition of the Wasserstein 2 distance. So it's a linear optimization problem over the coupling set, over the space of probability distribution on the product space X times Y. So pi is a probability. And there are marginal constraints, which I denote by pi 1 is equal to p, which means that you integrate over y, and you should get p. You integrate over x, and you should also get pi q with pi 2. And so this is really a linear optimization problem, and you have the cost in the formulation, and for W2, it's taken as the distance squared. But here, I will be working on the Euclidean space, so the distance squared is the Euclidean distance squared. Okay? So let me consider a super simple case. What can I do best? And if I consider two Gaussian measures with identity covariance matrix, what differs between the two Gaussians, they only differ by the mean. So mu for the first one and mu plus delta for the second one. And so in the for the Wasserstein 2 distance, it is explicitly known that what I want to find is delta. So the difference of the two means, okay? So now statistics tells me that what I can do best to estimate this shift is really to compare the empirical means, okay? And so if I do that, by standard statistical estimate, you have an estimation which decreases like 1 over square root n with a multiplicative factor which is square root of 2d, where d is the dimension. And so it's slightly dependent on the dimension, but not too bad, okay? And this is minimax optimal. It means that you cannot beat it. Okay, so the best we can hope for is to have estimates in 1 over square root n. So please feel free to interrupt me if you have any questions. So this is the best we can do. And so this is super simple situation. So there is another situation where we have this 1 over square root n convergence. So this is the case of kernel-based distances. So the setup here is that you consider a space of functions which are continuously embedded in the space of continuous function, so that Dirac masses are in the dual space. So by duality, it defines a kernel, k of x dot, is the representer of the Dirac mass, delta x. And so now you can measure you can measure the norm of a probability measure just by saying that they are in the dual space of your Hilbert space. Okay? And there are nice explicit formulas for the norm of mu being a probability measure. And it only depends, so for instance for mu hat, there is an explicit formula, the sum over I and j, of k xi xj. And so what I want to say here is that if you want to estimate the norm between mu and mu hat, what you obtain is a rate of 1 over square root, which is nice. And here, the 2D, the previous 2D, is replaced by the subnorm, the supremum norm of the kernel. Okay? So it's, but here, the dimension does not directly appear. The dimension, the ambient dimension of the measure. So it's completely hidden in the kernel. But this is a nice Monte Carlo rate. Okay? Okay, and now look at if I change the space of functions with which I'm going to compare mu and mu hat. So I switch to a reproducing kernel of the ball of a reproducing kernel to a ball of Lipschitz functions. Then, okay, the class has changed. There are many more functions, okay, in a sense. And so the estimation, so this is called a W1 distance. So this is the Wasserstein 1 distance, and it's well known that the estimation is cursed with the dimension. And what I mean by that is that the rate goes like 1 over n to the power 1 over d. Okay? And so there is nothing to do. You cannot, it's sharp, in particular if P has density with respect to Lebesgue. And the rate is super slow if D is large. You compare with 1 over square root n versus 1 over n to the power 1 over d. Okay? So now the goal of this talk is to construct an estimator of the Wasserstein distance between P and Q, just having the knowledge of Pn and Qn, the empirical measures. Okay? Okay, so the first naive idea you can use is the following one. So you take Pn and Qn, you compute the Wasserstein distance between Pn and Qn, and this is your estimate. So this is computationally feasible because the cost is n cube log n. But the problem is that the estimator is cursed with the dimension, and it behaves like 1 over n to the power 1 over d. Okay? And of course, we need assumptions in order to propose an estimator which is nice. And the assumption that we are going to make is that we are going to assume that, okay, most of the time, smoothness enables you to get rid of the curse of dimension. So here we are going to assume that what we want to estimate are smooth functions, namely the optimal potentials are smooth functions. And we are going to use a sum of squares approach on reproducing kernel Hilbert spaces in order to define the estimator. Okay? So what was the state of the art 2 years ago? So maybe you know about entropic regularization. So you can say, oh, I'm going to regularize my problem, and then I'm going to adjust the regularizing constant in order to estimate the true underlying optimal transport problem. But it doesn't work. It's also cursed with the dimension. Then you can try to use entropic regularization in order to fasten the computations. And this does work. Okay. But still, it's a bit better. So this is a paper by Shiza, and I'm also on it. Okay, but there is still a bad D rate in it. Then, a few years ago, Hutter and Rigolet have shown that minimax rates for estimation of smooth optimal transport, but they did not propose any computationally feasible algorithm, because they had to project on a particular set of functions, which are convex functions and so on. So it was not feasible. Smooth and convex functions. And now, and Weed and Berthet propose to estimate using a wavelet estimator the densities, and then they resample from their estimation, and then they compute optimal transport using standard algorithm. But it's also curse from the there is a curse of dimension due to the computational cost. Okay, so now what do I mean by smooth optimal transport? So the first definition I used was the primal definition of optimal transport. Okay? So there is the dual formulation, maybe you know about that. And this, so you have to optimize on potentials, U and V. And so this is linear optimization under inequality constraints. And this constraint can be imposed on the whole domain. So this constraint is C of x, y should be greater than U of x plus V of y. And so we are lucky in optimal transport if we assume regularity of the data, if we assume regularity of mu and nu, assuming also that they are supported on a convex set, for instance. Actually, it's sufficient to only suppose that one of them is supported on a convex set. Then you have regularity of the minimizers, or the minimizer, the unique minimizer of the dual functional. And what we are going to assume in this talk is that the optimizers U star and V star are in a Sobolev space of order greater than the critical index for the product space RD times RD. Okay? So it's D over 2 plus 1, D over 2 times 2 plus 1. Okay, so now I'm going to explain how to use sum of squares in order to leverage smoothness. So first, the problem in the dual formulation that I presented is essentially the constraint, which is an inequality constraint, which has to be satisfied on the domain. And if instead of an inequality we had an equality, it would be much nicer, because you know that you can trade smoothness, you can use smoothness in order to get rid of the curse of dimensionality. So let me consider the following problem, which has been treated in the literature by, for instance, Wendland and Rieger. So you consider omega a domain of RD, and you consider a sampling set X. So you have X1 to Xn. These are your samples. And there is a H, which is the field distance. I need to define the field distance, which is essentially the largest, the radius of the largest ball you can put in your space without touching your sampling set. Okay? And then now consider the following problem. You are given f, a function f, that you know it vanishes on points x1 to xn. Okay? And what you'd like to estimate is the subnorm of f on the whole domain. And in order to do that, you can use this nice inequality, 5, equation 5, for which tells you that essentially if you have smoothness of f in a Sobolev space of regularity S, you have this nice inequality. And there is still an important point here, is that you need H to be small enough. And the problem here is that in order to make H small enough, you need to have sufficiently many points in X. And so it behaves like, so the number of points you actually need behave exponentially badly in the dimension. Okay? But as soon as H is sufficiently small, then you are in good shape and you can apply this kind of inequalities. Okay? And now, we want to apply this on the inequality constraint on the dual problem of optimal transport. And what we want to control is essentially the infimum of the dual constraint, the inequality constraint above here. So what you can do naively is to subsample the inequality. You impose the inequality on the sample set, and you hope to get bounds on the infimum of this inequality. And if you don't have smoothness, you are bound to Lipschitz inequalities, which get you to the curse of the dimension. Another way to go would be to work on Fenchel-Legendre pairs, but we were not able to do it. Maybe it's possible to do it, but we were not able to do it. So one solution, when it's possible, is to replace inequality by equality. Okay? Super nice. And this has been proposed a while ago by, and in particular developed a lot by Lasserre, Henri, and many people. So in particular for global optimization. So the problem they looked at was to optimize a polynomial function on a set which is also defined by polynomial inequalities. And under mild assumption, you need a structural result here, which is called the positive Stellensatz. You can minimize a linear functional on your space of polynomial. You can minimize a linear functional on the coefficients, subject to constraints, and at least an optimizer satisfies that you can write it as a sum of squares. Yes. And in fact, until recently, all this literature was restricted to space of polynomial functions. But in fact, sum of squares can be applied in different settings, and in particular in reproducing kernel Hilbert spaces. Okay? This has a long history in analysis. For instance, it was proposed by Pfefferman a while ago. And also, it was studied by Boni for functions and operators. So if you have f of x which is non-negative, what you can do is represent it as a sum of squares just by taking the square root. Okay? So what do you lose here? At least one thing you lose. It's clear that at least you lose regularity. Okay? Square root of f, it's not clear that it has the same regularity than f. And that's the problem, because it means that you enlarge the space of functions you are working with. So for instance, smoothness, there is a result by Boni which tells you that if you start with a C2k function on an interval, which is non-negative, then you can write it as a sum of two squares, but what you lose is regularity. Okay? So it's not given that you can still optimize on a space of nice function when you write it as a sum of squares. And so you need to work a bit to find this kind of results. And so in our case, what we're going to assume is that maybe it's possible to write our non-negative functions as a sum of squares, which we can rewrite in reproducing kernel Hilbert space as a positive operator A applied to the kernel of the product space. Oh, okay, so, and I forgot to mention an important point. This sum of squares idea on reproducing kernel Hilbert space has been applied in optimization and developed a lot by Rudy, Marteau-Ferret, and Bach 2 years ago. So now, for smooth optimal transport, we do need a structure. We do need to represent, at least for the optimizers, U star and V stars, as a sum of squares. We need this C minus U star minus V star to be represented as a sum of squares. And this is, in fact, this is not difficult to prove it. What you use essentially is a Taylor expansion plus Cholesky decomposition. And so, yeah, second, you take the square root of the Hessian along the optimal transport plan, and you get the result, essentially. And what we need is the strong convexity of the optimal potential F star. And for that, smoothness assumptions are also important in order to have this right-hand side H to be sufficiently smooth, okay? And to be contained in a reproducing kernel Hilbert space. Okay? So now we can define a formulation, an estimator. So in the continuous formulation, when we have access to all mu and nu, this is simply the dual formulation plus a regularization penalty on the norm of U and the norm of V in the corresponding reproducing kernel Hilbert space with a penalization lambda 2, which we're going to adjust. And we need to penalize the trace of the SDP operator A. Okay. Okay. And we have now, we remove this inequality constraint by an equality constraint. And we are okay to do it because we know that the optimizer satisfies it, okay? Okay, but now we need a sampled formulation. We simply replace mu by mu hat and nu by nu hat. And now we also sample the equality constraint using just a given set of points. And we, so assuming that we are able to solve the previous formulation, at least computationally, we can define an estimator, for which we have certain inequality which ensure convergence. Okay. And now what's interesting here is that we are using reproducing kernel Hilbert space. We have nice associated kernels, and we can reformulate the previous sampled formulation, sampled estimator, using the kernel trick. And in this formulation, we can reduce the optimization problem to an SDP optimization problem, which we like to write in the dual form because it's better behaved than the primal, a bit better. We can compute everything, and we can estimate the computational complexity. We are using interior point method, and we can track the complexity. And so instead of looking at this particular slide, the main point that I want to make here is that remember the first case that I presented with Gaussians. So if you take n samples, small n samples, and you set accuracy epsilon is 1 over square root n, which is what I presented, we have a cost, computational cost. When we assume that the regularity is super high, we have a cost of O of n squared. So it seems like we have solved the problem. But in fact, the curse of dimension is still present in the constant. And in order for this result to really apply, we need to have a lot of samples if the dimension is high. So in fact, the curse of dimension is present in the constant. So now we can do a bit better. So this was for the estimation of the Wasserstein 2 distance. And now it would be nice if we can prove quantitative estimate on the potentials. Okay? And the potentials are simply defined by a convex minimization problem. So maybe you can hope to prove something on the argmin. Huh? Okay? So what can be said on potentials? Hutter and Rigolet worked on it in order to prove minimax rate of estimation. And look at what they study. So they take mu, the first measure, and they look at the L2 distance between the optimal maps. between the optimal maps nabla F star. So you need to know a bit of optimal transport, but I think it's okay. So nabla F star is the map which sends mu to nu. And nabla Fn is your estimator of nabla F. Okay? And the best you can do is essentially to have an estimate if M is the smoothness of the data being mu and nu. You know that if you have smooth optimal transport, the map is smooth M plus 1, okay? Cm plus 1. So best you can do is n to the power m plus 1 and divided by m. So if m is super large, it's essentially 1 over n. And it's a bit strange because we are used to 1 over square root n rate, but the point is that this is integrated with respect to mu, which you don't know a priori. So it's L2 norm with respect to mu. Okay? So in our framework, we achieved 1 over square root n rate of estimation of the W2 distance. So now if we want to have estimation on the argmin, we need a bit of, usually a bit of strong convexity. So a priori, you start from the dual formulation, which is linear optimization under linear constraint. There is no strong convexity. So first trick you apply is to optimize on the second potential. We would like to, okay, so we would like to estimate, so if you get back to this formula here, you see that you want to estimate, to optimize on a linear functional, which has two arguments, f and g, okay? So you can pre-optimize on a given variable g, for instance, in terms of f. You fix f, you optimize on g. And if you do so, you get a better behaved convex function, which is called the semi-dual functional. So in the case I study, it's the square distance, but it can be reduced to the dot product between x and y, because x squared and y squared, they are some sort of null Lagrangian in the cost. Okay? So you get rid of that. It's equivalent to this problem. And so here you can pre-optimize on the potential f. You get f star, the Legendre transform. It retains more convexity. So this is the kind of bound you can prove. So you see that by having estimates on the semi-dual, you have estimates on the L2 norm of between the maps. But L2 norm with respect to mu, okay? And now what's a bit strange is that we have estimation on J of f of the order of 1 over square root f n. And we need to pass to a better estimation of this difference in order to get to the 1 over n rate. And to do that, so this is what I say here. Equation 28 is essentially what we have. Equation 29 is what you get using kernel norms. So you have also 1 over square root n, fluctuation in 1 over square root n. And then, a priori, you cannot do better than 1 over square root n. But just using a bit of massaging a bit the inequalities. So for instance, if you are interested in J of nu of Fn, if you are interested in the first term, what you're going to introduce is the sampled measures mu n un in the game, and you can rewrite it as a sum of scalar product between mu and mu n, which fluctuates in 1 over square root n, and f and fn, which also fluctuate in 1 over square root n. So you can imagine that you pass to the 1 over n rate. But to make this work in practice, we also need regularity assumptions, and we need to use Gagliardo-Nirenberg inequality to make it work, but that's technical details. And due to this Gagliardo-Nirenberg inequality, we are not able to get back to Henri rate, but almost, up to a factor epsilon, which is shown here. So the epsilon here is due to the Gagliardoni-Ehrenberg inequality. If it weren't present, we would get the optimal minimax rate. So in conclusion, we were able to leverage smoothness in optimal transport using sampling inequalities by applying sum of square method in reproducing kernel Hilbert space. But be careful. So we were able to reduce it to an SDP formulation, which can be computationally done. The point is that there is no free lunch here. The curse of dimensionality is not present in the rate, but it's still present in the constant. So we need, in fact, a sufficiently large large number of points, depending on the dimension, in order for this inequality to apply. Okay? So maybe it can work. So we did some numerical experiments. So maybe it works in, let's say, a rather small dimension, 5, 6, 7. But to go above, it's a bit hopeless. So any questions so far? Yes.
I'm sorry, I might have missed something. So basically, the formulation you have is coincides exactly with SDP, right? So it's not the sequence of relaxations, it's a bit.
Yeah.
Okay. And in practice, like small dimensional is still computed.
Yes.
But
in fact, the number of points. So it really depends on the number of points with which you're going to sample the inequality. Okay, so this is the bottleneck.
When you say that the constant is the dimension is in the constant, it's the dimension of the space.
No, it's the so in fact, in order for this inequality to apply, so the Wendland and Rieger inequalities, sampling inequalities. This is the key word. You need to sample your domain with an exponential number of points. Exponential in the dimension. And so this is the bad, but there is, I mean, okay. Okay. So now I'm going to switch to a second result. And so the first result was published at Colt, and there is a companion paper which is currently submitted. And now I'm going to present the work of Raphaël Barboni together with Gabriel Perret. It has been published at NeurIPS this year. And the question we want to address here is the question of global convergence of a particular structure of ResNet. So here, what we want to do is essentially to look at the standard setting of supervised learning. Okay, so you have a function f which depends on parameter theta, which you're going to apply to samples xi. And you hope to minimize the true loss functional, which is defined by G here. And in fact, what you do is to minimize the empirical risk defined by L theta, and you want to minimize it, okay? And to do it, you use a standard gradient descent algorithm, and you can find theta star, or at least estimate of the minimizer. And what's important, in fact, it's the question of generalization, which is essentially try to actually minimize the actual true functional G instead of L. But this I'm not going to talk about. I'm just going to talk about the minimization of L. And, but for a particular structure of F theta, and F theta is the composition is going to be a ResNet. So it's a particular case of a deep neural network. Deep neural network is simply the composition of a single hidden layer. The single hidden layer, for me, it's the composition of two linear maps, theta 1, theta 2, and in between you have a nonlinearity, which is applied pointwise. And if you try to do it, even in the linear case, it's kind of super hard to converge in practice. Maybe because you are just composing n times with something. In the linear case, if you assume that your single hidden layer are simply linear maps, you have simply a product of matrices. And you know that to make it of order 1, it's much better to make it close to identity. So if you make it close to identity, you can try to write as a particular structure, try to write instead of as a single hidden layer, you write it as identity plus a residual f theta. And it makes your life much easier when you try to optimize on it, and it was a very successful architecture. You can look up at the number of citations of the paper. And what's super funny is that it resembles to an Euler integration scheme. And this is the structure. This is the structure I want to say something about in terms of optimization. And so, just a glimpse at state of the art. So it's been a long time that I haven't read the literature on it. So many people are working on it. So for me, it's impossible to give a proper account of research here. What I can say is simply that the benefit of over-parametrization, sometimes it enables you to get the loss to 0, even on random data. And the key info from deep learning is that it's not harmful for generalization. Okay. So, in the case of over-parametrization for a single hidden layer was written by Shiza and Bach and also Montanari and co-authors. And so, the idea simply is that you're going to represent your function f, your single hidden layer, by just the integration of a measure over the parameter. So you transform it into a linear function in terms of mu, which is now your parameter. You transform something non-linear into linear, but you pay a cost. And so that was studied by the so-called neural tangent kernel, which is essentially a sort of linearization of the problem. And they are able to show global convergence in these two cases, the case of a single hidden layer when the width of the number of neurons goes to infinity, Shiza and Bach. And when for a proper initialization of the weights of the thetas, in some situation you have the initialization is sufficiently well done so that the optimization scheme will tend to stay in a neighborhood of the initialization, and this is called the neural tangent kernel. So it's a kind of linear regime. And so far, if I understood correctly, or at least 2 years ago, when I started to be interested in this topic, only the shallow neural nets were treated and the linear regime. So we wanted to say something on the nonlinear regime. And in this configuration here, the key tool for optimization is the Polyak-Lojasevic inequality. It's super nice inequality, which tells you exponential convergence. So if you want to optimize a function f, and you are given a nice Polyak inequality, Polyak-Lojasevic inequality for t, so you can measure f minus f star, where f star is the minimum, by the gradient squared of the norm. So if you have that, you get for free exponential convergence, and the point is that you don't need any convexity, a priori, to apply this kind of result. You don't need Euclidean structure as well, neither. And it applies, for instance, to Riemannian manifolds. So super interesting. And a particular example of it is the log-Sobolev inequality, which tells you that if you minimize the Kullback-Leibler divergence and you do Wasserstein gradient descent, you get exponential convergence. But the problem is to establish this inequality. It's not for free, and most of the time, in fact, you get back to standard convexity in some coordinate system. Okay? And, okay, but still it's interesting. It's interesting in particular because you can change coordinates. And Poiliak-Lojasevich's inequality is stable, is robust. You change the constant, but still it's robust with respect to change of coordinates. if you have a bound on the gradient of the diffeomorphism. Okay. But a priori, it doesn't tell you the convergence to the argmin. It tells you a convergence on the value. So the setup we are going to look at is the following one. So you have a simple ordinary differential equation. Q dot is equal to f theta of q. And at the beginning, we precompose by A a linear map, and we postcompose by B another linear map. Okay? We assume, and this is the important assumption, we assume linearity with respect to the parameter. So you may say, oh, okay, it's going to be super restrictive. But in fact, linearity with respect to the parameters, you can assume that you have, for your family of f theta, you can assume that it's in a linear space, like Sobolev space. So still, it can still encode diffeomorphic flows. So in some sense, it's going to be super expressive. At least it's going to be universal in the space of diffeomorphism, in the connected component of identity. And if you are not happy with it, I can tell you that I can turn f theta, which is a shallow hidden layer, by doubling the dimension into a neural ODE, which is of the kind I mentioned, which is linear in the parameters. I make in fact the hidden layer not hidden anymore, but by doubling the dimension. So I do think that, in fact, so this model actually captures the nonlinearity of deep networks. And for this model, we are able to show that it satisfies a sort of local Poiliak-Lojasevic inequality. And so the analytical setup is the following. So I pass to a continuous time problem. So I integrate the solution of my differential equation, which is driven by a vector field xi here in equation 45. So I integrate the flow, starting from identity at time 0. And what I need to assume for the result to hold is an embedding of the space of vector fields into W2 infinity. So it means essentially that I can differentiate twice, and they are continuously bounded. Okay? And now you can look at the group of all these flows at time 1. And in fact, it has been proven a while ago by Trouvé that this set of flows form a metric space which is complete under this right invariant distance. Okay, so what I mean by right invariant distance is, by definition here, just the L2 norm in time of the vector field, of the norm of the vector field in the reproducing kernel Hilbert space. Okay, now and you use backpropagation to compute the gradient, or can use adjoint equations. And so if you look at the adjoint equations, because we want to get a Poiliak-Lojasevic inequality, so we need to compute the gradient to estimate the loss versus the gradient. And when you look at P at time 1, which is the co-adjoint variable with the adjoint variable of Q at time 1, it encodes essentially the loss up to the composition by B star. Okay, but it's essentially the loss we want to minimize. So in P at time 1, you have all the information on the loss. So now, once you solve the backpropagation equation, the adjoint equation on P and Q, these are kind of Hamiltonian equations, then you can hope for estimates on the loss. And this is essentially what we get. Essentially, you can say that, oh, you have the loss, but what we do is a sort of diffeomorphic transformation of the loss. So it's in a sense, it seems to be a bit natural to achieve local Pollack-Lojasevic conditions. So we do need assumption on the kernel. We need the kernel to separate the points and to be sufficiently expressive. But using these assumptions, we are able to show this inequality 52 and 53, which tells you that it satisfies Pollack-Lojasevic. So in particular, the benefit of this overparametrization here is that all the critical points are global minima. Okay? And if the initial loss is small enough, then we get global convergence. The problem is that we only have a local Pollack-Lojasevic inequality. And so it tells us that if the iterates of the gradient descent are bounded, then it's going to converge exponentially to the minimizer. But we don't know a priori how to have guarantees on the fact that the iterate is going to be bounded. Okay? In fact, even if you look at the linear case, we are not able to prove global convergence because it does not hold. Instead of assuming that I have functions defining my velocity field, I simply say that I have linear maps, okay? So I just look at the flow of matrices, okay? And it's not possible to prove global convergence, and still they are critical. In fact, it's possible to converge to. Okay. Okay. So, sorry, I should have prepared the talk a bit more. So what I want to mean is that if instead of minimizing this continuous flow, instead of using this model, you use a completely discrete model in the linear setting, then you don't get this local PL property, but you still get critical points, and which are not global minimizers. And in fact, by doing this overparametrization in time and continuous time, you take all the critical points which are unstable and you put it to the boundary of your space. Essentially, this is the spirit of that. So we can enforce global convergence by using high-dimensional embedding to still come up with a result. But our high-dimensional embedding needs an M. M is the number of dimension we multiply the ambient dimension. And in fact, the M, the dimension we need to embed our data is super, super large. So I think it's not really super interesting to look at this inequality, but still it guarantees some global convergence results. But I do think what's more interesting here is to try to come up with a proof of global convergence with respect to almost sure initialization or global convergence of stochastic gradient descent, which we were not able to prove. And as I said here in blue, just the simple question of global convergence cannot be solved without any embedding. And probably the answer is in the linear case, because in the linear case, there are probably almost sure convergence, but we were not able to prove it. And there are open questions we are interested in, so if you have any insight on it, it would be nice to discuss. Even in the linear case, when I'm looking, instead of group of diffeomorphism, I'm looking at just the linear group. We were not able to prove global, almost sure convergence in initialization. And also it's the case of normalizing flows. It's connected to our setup here. And if we make a gradient descent in the case of normalizing flows, by linearization of the problem, we get back to the Stein variational gradient descent, for which very few results are known analytically in terms of convergence. So I would be interested in this as well. And also, pay attention that we said nothing on any regularization of the problem. So if instead you use weight decay, so L2 penalization of the weights, we have no results. We really have no results. We really need this regularization to be set up to 0. And this should not come as a surprise, because essentially when you do it, when you do weight decay in this setup, what you end up with is essentially geodesics as minimizer on a group of diffeomorphism, and it seems to be super non-convex, and not even PL. And so with it, I think it's time for questions.